This in the back of that last paper we left off on, the molecular polarity. And we're going to do some examples. Okay. Now, I want these kind of problems basically take several. They have several places you're going to screw up. All right, several parts to these problems. The first place you're going to have a hard time getting the correct answer is with the electron dot notation. I'm not going to work on that today. That's tomorrow and Friday. We're going to spend time doing the really difficult electron dot notation. Okay. So I don't want to talk about that right now. What I want to talk about today is the second part, which is the shape. Once you have electron dot notation, can you tell what the shape is and how that affects the bond polarity, molecular polarity, okay? So I'm just going to use generic letters. I did not do this with the other class in the afternoon yesterday first. Probably should have. Realized afterwards, probably should have done this, okay? So let me show you something. Say when you're done, you have an electron dot notation that looks like this, okay? Write that down for your compound. All right. This is a very simple question. There it is right there. You're going to be making a model. And remember, a line, or a pair of electrons, a shared pair of electrons, is represented by a line. I could just as easily, don't do this, I could just as easily have written it this way, with just a dash between it, right? But a pair of electrons, either way. Here's my question. What shape is that? It's amazing that people wouldn't get this right. It has to be linear. 2 points in space can only be separated by a straight line. So this guy is linear. All right. Now, really, I'm not probably even going to ask you one like that. Usually you're talking about a guy who has more than just one bond in him. But it is amazing how this will confuse people on this lab in particular. If I have only one bond, people, I've said this before, I'm saying it again now. Whatever that bond is, that's what the molecule is. There can't be anybody pulling opposite, can there? Look at it. Yet I will have people. I had it yesterday. It happened even though I thought I warned them enough. I'm going to warn you even more about it. If you only have one bond, it doesn't really matter what he is. If I look at if the bond polarity is polar, the molecular polarity is polar. But just as easily, if the bond polarity was nonpolar, the molecular polarity would be nonpolar. I'm just making these things up here, okay? And of course, what's the angle for a linear molecule? It's going to be 180. All right, now let me erase this next one. Actually, I can probably keep it because I could use this next one. Does it matter if the guy looks like this? No, it makes no difference. So, for example, the difference would be if I were to use these examples over here. Don't write this down; it'll just mess up your paper. This guy over here will be the equivalent of being like H, like where I don't have any other electrons around him. And here I would have like HCl. It doesn't make any difference, does it? It's still a linear molecule. It's still 180 degrees. And if this bond were polar, this would still be polar. It doesn't make any difference. Okay? So I'm just going over the shapes. I'm starting with two very, very easy ones. All right? And again, it wouldn't have mattered if this said nonpolar. If this said nonpolar, that would be nonpolar. Makes no difference. Okay. Now, let's get to some, obviously, that's not what I want to spend most of my time on. I just wanted to go over that because, believe it or not, that was a factor. And it probably will be for you guys, too. Two atoms, whatever this is, this is. It's as simple as that. I say that. I said it yesterday. I say it again today. You'll go back there. I will come around and set one of these set one's very easy of the ones you have to make. You're going to have a mistake. Somebody's going to write polar here and non-polar there. Oh, I thought it's symmetrical. How can one bond be symmetrical? You can't be symmetrical if you only have one bond. All right, now, time for the harder ones. What if I gave you a guy like this? Oops. Okay? I give you that guy. And I tell you those are, I'm going to tell you that you look up the bond polarity and it's polar. Okay? Well, what's the shape of this guy? How many, this is what the question always becomes. How many things are bound around the central atom? And the answer to that question is what? 4. 4 electron regions are bound around the central atom. Now, granted, only 3 of them, 1, 2, 3, have atoms associated with them. One of them is just an electron pair. So the shape would not be tetrahedral, even though you would think it might be. It's going to be tetrahedral without the top, which is trigonal or triangular pyramidal. And like I said, I've been finding that at least online, the ones I've been looking up, they use the word trigonal rather than triangular. I think you all have to say it's the exact same thing. Trigonal or triangular pyramidal, trigonal or triangular planar, same thing. You may see either one on the test. All right. Trigonal pyramidal, and is this shape symmetrical? No, it's not. All right, so if I have a polar bond here, what kind of molecule do I have? I have polar. It is not nonpolar. The exception is when they are symmetrically arranged. All other things being equal, you got polar bonds, you're going to have polar molecule. You have nonpolar bonds, you're going to be a nonpolar molecule. The only exception to that is if I have polar bonds and they're symmetrically arranged. All right, let's do a couple more. What about this guy? What would I call this guy? This is a tetrahedron, right? Because I've got 4 atoms bound around a central atom. All right, so that's going to be a tetrahedron. And if I told you that this guy was polar, what would you say the molecular polarity has to be then? Non-polar. Good. All right, so hopefully you're getting this. By the way, what were the bond angles for these guys? Around. This is 109.5. This one's not exactly going to be 109.5, but around 109.5. It'll be close to that. It won't be exactly the same because instead of having an atom above it, well, not above, but in this position, it has just electron pairs. So it'll be slightly different, but it'll be around that number, okay? Because it's basically the angle of a tetrahedron. Very, very close to it anyway. All right, let's keep going. What if I gave you this guy? Okay, that guy right there. I circled him so you don't get him mixed up with the guy above him. So that's what he looks like right there. Okay, right here. Just what's in that box. What shape would that guy have to have? He would be a tetrahedron without the top. Okay, here's your tetrahedron. Because there are 1, 2, 3, 4 areas. But there's 2 dots, I just didn't see them. 4 areas around that guy. So I take off the top. I take off one other side. And I'm left with a bent molecule. Okay? With, again, bond angles are going to be around 109.5. But bent is the answer. Around 109.5. It won't be exactly that because it's missing, it doesn't have 4 atoms around. They're not identical. Now, if this were a polar bond, what would the molecule be? It would still be polar. Because this is not, bent is clearly not symmetrical. One guy's, there's going to be an up or a down to it if we're looking at it this way. Okay, one side is going to be more negative than the other. And the other side is more positive. I have to erase the board to give a few more. What would this guy be? I'll start using dashes. Okay? What would that guy have to be? If he's got 3 things bound around him and no electron pair up top here. He would be trigonal planar. Yeah, like this guy right here. Okay? Trigonal planar. He is symmetrical. So if I have polar bond angles, by the way, what would the angle be for that? 120. And if he were polar, so would the molecule be polar. Wouldn't it? Come on, people. No, it would be nonpolar. Come on, you gotta be thinking. You can't just be writing things down. Right? Why? Is this symmetrical? Yes. Yes, it is symmetrical. Which, again, see how it's happening? I mean, so if I'm going to draw it as it exists here. B, A, A, A. If this guy's pulling that way, these guys, their vertical component is going to be identical to that from these two guys pulling that way. And the same thing is true for this one and that one. All right, so even though he wants to pull these electrons closer to him and he wants to, fact is, he can't because they're all going to cancel out. So it's going to be non-polar. Okay? Got it? Again, this is what happens. We kind of get into this funk of, just writing stuff down and we're not really thinking about it. All right, one more I think I have with this. Okay? And this is an interesting one because it does show up on the lab we're doing in a minute. What if I gave you this guy? I'm going to use, I just rewrite it. What if I gave you that guy? Well, the shape is easy. What would the shape be? Tetrahedral again. I have four things. However, let's take a look at this guy. I've got four things, and that's a symmetrical shape. Okay, tetrahedral. And the bond angles are 109.5. However, is this a symmetrical molecule? No. All right? That's why I wrote B, 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 and C. They have to be identical things around that. I'm assuming, since I've written a B here, that it's not the same thing as a C. So this guy's not pulling as hard as this guy, perhaps. They aren't the same thing. Right? As a matter of fact, you would have two answers for this, wouldn't you? You would have an answer for this, for the bond polarity, and you'd have an answer for these bond polarities, right? So let's say that one of those bond polarities was polar, and the other one was non-polar. It really doesn't matter which one's which. The answer to the question, is this molecule polar or non-polar, is easy. What would the answer be? Is this molecule polar or non-polar? Polar. Because although I have a symmetrical shape, I don't have identical things around it. So let's say that's the polar bond. He's pulling harder. These guys aren't pulling at all. There's going to be a charge difference. All right, so he's going to be polar. All right, so that covers, just in general, some of the shape stuff. Remember I told you there's like 3 parts to this, okay? One of the other parts is, and I'm going to just take a few seconds because that was also a problem for a lot of people. What happened there? I'm going to do that. I'm going to take a second to do one other thing. Electron dot notations. I'm going to spend a lot of time Thursday and Friday going over these and doing some practice ones. But electron dot notations, for easy ones, we've only done them the easy way. So if I've got H, and I'm going to add him to BR, and we do electron dot notation, all I cared about, all I ever told you to do was just try to make everybody happy with an octet rule. Okay? And not everybody wants an octet. There's a couple of exceptions. Hydrogen happens to be one of them. But if obviously the hydrogen, like a puzzle piece, went up here and he shared those electrons, that's what he looks like. So no one would be surprised that that is the electron dot notation for HBr, right? Yeah. But here's the problem. My guess is on your lab right now, take them out, get them out right now. The ones that you did half of about 3 days ago, okay, on the left side, you did the 2 columns on the left. Take those out. It says molecular or covalent molecules or something like that on the top. All right. No, wait. Just wait. We don't really have extra time here. So if you look down there on the front side now, we're on the front side, you'll see like, oh, these are easy. What's the very first one it asks you to do? What 2 elements? H? H and H? Okay, so it'll be done. And what's the next one? Cl and Cl? Okay. So H and H, no problem. Cl and Cl, no one's going to have a problem with this. But if this is what you have for O and O, you probably don't realize it, but that's not correct. That is not right. Okay? Does anybody want to see why? Well, let's see. If I drew O over, and again, this is what tomorrow and Friday are going to be about. If I drew O over here, I would find that he looks like that, and another O looks like that. And everybody's okay with that over here, right? Those are an individual O electron dot notation for both of them. What's the problem writing your electron dot notation like that? Too many electrons. Kind of the same thing that happened with my carbon dioxide yesterday when I was explaining that one, right? Anybody have a solution for this? Yeah, we're going to have to use a double bond. So actually I have to share 2 pairs of electrons between them. Okay? All right? Now, how many are left over to actually fill up for an octet if I want to follow the octet rule? Well, he's got 2 being shared here, so I would need 2 more. That's 2, 4, 6, 8 for that guy. 2, 4, 6, 8 for that guy. See? You're sharing like that. And that is how you would draw oxygen correctly. All right? Same thing happens in a couple of other ones throughout. Okay? It happens in about 2 other places on that lab. I know I'm asking you to do, the lab is mostly about the shapes, like the previous one, stuff I was doing today. So I don't want you to get hung up on the electron dot notations. Most electron dot notations are easy enough to do with just using the octet rule. But there are a couple that are tricky. And I'll tell you right now, right below oxygen is another one what's going to happen. All right, I'm going to stop the video here for a second. So I'm going to tell you about the lab.